Hey class, so let's work on the next unit, 3D graphics. Now 3D graphics are kind of like the real exciting point for many people when it comes to computer graphics. 3D is where things got exciting. When games got 3D, when movies got 3D, it's where people get really into it. So a lot of people find this unit very interesting. Now of course, we've kind of touched on 3D throughout the whole assignment. We've talked about working in 3D and we've talked about a bit of projection. So it's not exactly like we've ignored 3D, but now we're going to delve right into 3D and talk about all the specifics and all the challenges that come along specifically for it. So there's two things. First, I want to talk about two different approaches to rendering in 3D. So we've talked about some, but I'm going to break this down. So rendering in 3D. There are two classes, basically two main approaches, and they're quite different. They're quite different. So if we have, starting with a scene that's already in 3D, so given a scene full of 3D geometry, how do we turn that into an image? Oops, that's of. How do we turn that into an image on the screen? Now, one way is called rasterization. And if you've been following the course, that's basically what the whole course has been about so far, for the most part. So we use transforms to go from where the object is to our raster. Where objects. Right? So we have these things in 3D space that we have defined in 3D space. Let's say I have like a triangle and a circle, and then we have this raster here. That's supposed to be a square. We have this raster here that you're looking at. This is your eye. And what we do is we go, okay, I have a triangle, and you go through all these transformations that we've talked about in order to bring it onto the raster. The same thing goes for the circle. We figure out, okay, object space, world space, camera coordinates, we project it onto the raster. And then once we know where it is on the raster, we for the final mile, we use rasterization algorithms. To choose which pixels to light. Okay. So this is what we've done so far, basically. What we've been doing so far. Now, one of the benefits of rasterization is that it's lightning, it's very fast. Okay? It's very fast, and the reason why it's really fast is because it's kind of like the minimum amount of work that we need to do. I have a triangle, let's figure out where the corners are on the screen, let's fill it in as quick as we can. So it's fast, there's a lot of room for shortcuts, a lot of places for shortcuts. And to this day, for anything that needs to be fast, like a video game, even a lot of what happens with the big 3D movies they take this approach because it's just that fast. Of course, there are limitations, and the biggest ones are it's a little tricky to do things like shadows, reflections, soft lights. Soft lights are like, instead of having a hard shadow around something, it like blurs out like in the real world. All of these require special treatment. Okay, they require new consideration, new algorithms. And for the last 30 years or so, maybe 40 years by now, people were figuring out new techniques to emulate these features. Okay, So you can read books and books on tricks. You know, environment mapping is one that gives reflections and all kinds of tricks we can do. So that's rasterization. We've talked about that a lot, but I wanted to highlight that we go from the object in this 3D scene, we transform it onto the raster, and we fill it in. That's rasterization. That's not the only way. There's a competing approach, which is kind of the opposite direction, and that's called ray tracing. The problem, if rasterization is we have objects, put them on the raster, ray tracing is kind of the opposite. So instead of working from the object to the raster, we cast rays from the eye into the scene and see what we hit. Okay, ray tracing. Instead of working from the object to the raster, cast rays. I'll put that in quotes. What does it mean to cast rays? It's a computer program, right? So we cast rays from the eye. And I'll come back to that. All that it means to cast rays is to figure out the math. But the idea, I think, is that you're casting rays into the scene. Let me show what a raycaster looks like. So here's a raster, okay? This is my raster. And I'm going to make an eye over here that's looking. And it's looking at the raster. That's my eye. Now previously, I'm going to draw it a little differently. Previously, we have this triangle here, we have a circle here, and we work backwards. But now we do a whole different approach. I take every pixel on my screen, okay? I go through the center of that pixel, and I make a vector from the where the eye is through that. I make a vector from my eye through that pixel, and then I solve for the math. I cast the ray into the scene to see what it hits. And I do this for every single pixel on the screen. So for each pixel on the raster, we cast a ray into the scene. Just see what it hits, okay? And basically, in this case, it hits nothing, right? If it hits nothing, pixel's black. Or maybe some background color you can choose. And what you do is you go through each pixel one after another. And so just a simple nested loop to go through every single pixel, make a new ray, and eventually, bam, right? You're going to hit something. Eventually you're going to hit something. If an object is hit with your ray, we just grab its material color. We've talked about materials already. And use it for the pixel. Okay, oops, there's a hair on my screen. So if an object is hit, cool. And then, but it's not that simple. If you hit an object, we grab its color, that's kind of neat, right? You can do that. But suddenly, other things start to become possible. If an object is shiny, for example, we can cast a reflection, right? So we can calculate the reflection angle. So imagine that this is a shiny sphere. When I'm going through this pixel here, I hit the sphere. Cool, I can grab its material, but look, I get a pretty stark reflection ray here. I can calculate that. Where's it going to go? So I calculate the reflection angle, cast another ray. Right? So I hit it and I cast another ray. So ray traces are typically done recursively for that reason. So I cast another ray, I cast another ray, and just keep recursing down. There's more things you can do. If the object is translucent, if you can see through it, Okay, you can calculate the refraction angle. And then what do you do with that, right? If I come through here and this is a glass ball, it's going to bend, right? Oops, it's refraction. I guess it doesn't really matter if it's an R. Refraction angle. We cast another ray. So again, recursive. In fact, in this case, the surface is shiny and refractive. So I might cast a ray for reflection, and I might cast a ray to go through, and those colors get mixed. And that's when you can see something like I can see through it, but I can kind of see the reflection on it, and they mix together. So that comes out naturally. Ray tracing also lets us do lights and shadows in a very different way than you did with Phong. Than you did in Rasterization. So you can still do Phong here. So lights and shadows. Okay. And because we have this ability to cast rays now, we can do all kinds of cool things. So let me draw another version of this. Here's my raster, right? And then, let's see. I'm going to draw a circle here. Let's see if I can get this reasonably right, like my notes. And I'm going to draw a couple of lights up here. Okay, it's my light. And I'm going to cast another light way over there. Let's try that. So I'm coming along, I'm going to my raster, and then calculate my reflection ray. We've already talked about that. But now I can cast another ray when I hit an object. I can cast a ray to a light. Okay? And by casting a ray from each spot that's lit to a light, I can do some really cool things. Cast a ray from the surface to each light. Okay, so I can do Phong or other model, right? Of course, it can take into account how far away the light is, that kind of thing. But look at this here. I want to highlight something here. This light doesn't touch the surface. It self-intersects, okay? It's behind it. So only one side of the surface gets lit by the one light, and the other side doesn't. The other side only gets lit by the other light. So to diffuse, you'll get them blending naturally there. But what's really cool, if you do it this way, is shadows naturally occur. Oh, this is supposed to say distance. You can make lights get dim as you get far away, that kind of stuff. So shadows naturally occur when another object is in the way. Now let me illustrate what that looks like. So here, if I'm casting rays to this thing here, right, I'm going to get these lights, but look, it's blocked. Okay, so I only get one light lighting the surface there. But then for here, I get two lights. So what you're going to get is when, let's change my color here to blue. When this light, here we go, this side here will be lit by this light. And you'll see a line where the shadow starts. And this here will be a shadow. And that happens naturally because I'm casting rays to seeing, can I see the light? If I can't see the light, I'm darker. If I can see the light. And all that you do is you just add together all the lights that you see. We kind of covered that in one of our activity classes. And you get this natural, shadow. And because of ray tracing, we're doing pixel by pixel reflections. It's a perfect shadow. Sometimes a little too perfect. So it's really cool. Now ray tracers, they're actually pretty easy to build. It's not a hard thing to do. Making a ray tracer, it's a common assignment in first year graphics, for example. I could give that to you as an assignment, and I'm sure we could figure it out. It's relatively easy to build. Okay. The hardest part, casting rays is easy. You just calculate the vector and come up with a vector, and then you need to intersect that vector with every object in the scene from the origin of the eye. So you just basically you come up with parametric equations, kind of like we saw with the line intersections, right? So parametric equations for the intersections. You can actually look this up. Line, intersect line with sphere, intersect line with plane, that kind of thing. So line, sphere, because of course our vector is like a line in space. You have a line, triangle, and a line and plane. Because we're doing this parametrically, the easiest shapes are the ones that have very clean parametric forms, right? Like a cone, like a sphere, like a plane. Triangles are a bit funny and take a bit more work. You have to intersect with the plane, then find out where you are on that plane within the triangle, but it's no big deal. But so ray tracing is actually pretty easy to do, the basics. However, there are ray tracing is expensive. It's slow. For example, you have lights, reflections. This all quickly because you're doing it recursively, I should put that in here. This becomes exponential growth very quickly. So it's very expensive to do. It's very slow. However, if you do well, you can get very realistic results. Okay, especially with anything with lighting and reflections, you get some really nice looking results that are hard to get with rasterization. Even now, real-time rendering is an ongoing goal. We're trying to do this faster and faster. Real-time rendering is an ongoing goal. You hear about now graphics cards that do real-time rendering, but what they're really doing is they're mixing and matching, and this is what we've been doing for ages. You can introduce certain things for ray tracing, other things for rasterization, and you can mix and match. So I'm going to jump over to my slides for a second here. Okay. Great. So this is an example of a ray trace scene. This is a classic, like, class assignment or old-fashioned ray tracing picture that you'd see. And the reason I say that is because the checkerboard is famous because it lets you see how things change. Look at the checkerboard is warped. We have a reflection here. And this looks photorealistic because you're actually using models of light and for reflections on surfaces, it works out really well. And then think about this for a second, the recursion. My ray is coming in, hitting the sphere. Cool. It bounces down and hits the box, which bounces down and hits and then how deep do you go? So if I look at the sphere here, I can see the green sphere, but I can see myself back in the green sphere, and I can see the yellow thing in the green sphere. That's 4 deep, exponential growth. The other thing that makes this obviously ray traced is the shadows. Look at the perfect shadows here. The light is above, and so whenever the sphere is blocking that light, okay, you get this is a hard shadow here. Another hard shadow there, and another hard shadow here. So this is classic ray tracing. Here's an example from my own. I built this ray tracer when I was a student, and again you can see the classic refraction back and forth here. You can see back and forth. Here I can see this, which sees this, which sees this, and you get this back and forth. It's very deep. This was 100 years ago, but this probably took about 30 minutes to render. This is a sphere in the background that's translucent without any refraction. I have triangles working. I have spheres and triangles. And this is, of course, Phong without a specular, it looks like, or a very big specular. And you see that nice fall off there for diffuse with the ambient color in the back. And this is a see-through sphere. Maybe I think the next one shows it a little better. Yeah, so here's the other pictures I did. And here you can see the refraction happening where it goes through and goes in, and you get this very photorealistic water type effects or glass type effects that you can do very easily or simply in ray tracing, but they're slow. It's very hard to do with rasterization. Here's an example that's more recent. People are moving games over to ray tracing, but what I see here that tells me there's ray tracing of these atmospheric effects where rays come in and you have things, particles in the atmosphere that interact with those rays and you get fog. We have these shadows, these soft shadows, and look here, you can see there's something in the way. It's not just lit up from the sun, but there's actually something in the way. There's something blocking my ray cast to the light source right there. So this is classic ray casting. And then same thing here, you have this reflection, and you have a blurry material, and you can do that with how you scatter the light and add some randomness and things like that. If you add randomness, you get that kind of thing. Yeah, so what you do here is when I reflect to the wolf, is it? Instead of just reflecting one ray, I'd reflect 5 with a bit of random perturbation, and I'd average them. And so I go, well, you scatter the light, which is exactly what happens in the real world. You scatter the light, you average them, you come back, and you get this blurry effect that you see here. Here's another example. So this is using strategies with cheats, basically. This is a technique called environment mapping with rasterization, and you can map textures from the environment onto your surface, and it actually looks pretty convincing. But it's not perfect, and where you see the differences are when it's driving, it'll look kind of fake, whereas with ray tracing it'll look real, and you'll have things like the eyes reflected here, which, bam, that they probably, if you wanted to do that with the environment mapping, you'd have to explicitly do every single thing. So ray tracing is pretty cool, and still kind of like a holy grail for video games and for movies, but it's still really slow. All right, so we'll leave it there, and we'll move on into more 3D in our next lecture.